Hello, I'm Emmanuel. Welcome back to Economics. From previous videos, we've been looking at regression analysis. We've tried to lay the building blocks and we've considered assumptions, even in the simple one, the classical linear regression model. And we also derived OLS estimators and we have looked at the properties behind the OLS method. So now we'll be considering a practical example, hypothetical one, and we'll be trying to estimate the regression function. That's the goal of this, or what we'll be doing up to this point, is to try to estimate the regression function. And now we'll be looking at two variables for a country. Let's assume Nigerian economy, and this consumption for different periods and the income in different periods. So we're trying to just graph this, not graph per se. So we'll be trying to estimate the regression function, where consumption will be treated as a dependent variable and income the independent variable. We're trying to just predict, say, in a given year, if income rises to this amount, what will be the change? What we expect in consumption to be. So in addition to that, we'll also be discussing a new concept, R squared. Looking at this case, let me just try to plot a random scatter graph where income is the independent variable, the explanatory variable, and consumption is the dependent variable. So assume on the scatter graph we have points, say something like this, right? With regression analysis, we can predict and sort of estimate a regression function. So we get as intercept coefficient and as slope coefficient, and that's what we'll be doing shortly. We'll be trying to use the OLS technique to get what our intercept will be and our slope coefficient will be. But now R squared makes things better because there are several times you estimate a regression function based on the data you have. But you want to see how well this regression function fits that data. Is it perfect? Does it explain it so well? And that's where the R squared comes in. Sometimes it's called the goodness of fit. So how well the regression function fits the data, or sometimes also called the coefficients of determination. Yeah. So we see this R squared. We've done something similar to this. You remember the Pearson correlation coefficient. So R squared is sort of in a way similar. In fact, if you square your Pearson correlation coefficient, you get your R squared. But it's in a way different too. The Pearson correlation coefficient looks at the relationship, and you can get something between a -1 and a +1. But if you are squaring this, your R squared can only stay between 0 and 1. If you have a minus something, when you square it becomes positive. So it doesn't tell you R squared doesn't tell you the direction of the relationship. You don't need that. You can get that easily with the sign of your slope coefficient. It just tells you how strong this line really explains what is happening in the actual data. So that's about R squared. Since this is a two variable case, we denote our R squared with a small letter r. But where we have more than two variables, where we have two independent variables, 3 independent variables, then your R squared will be a capital R squared, denoting a multiple case. Now, how do we then calculate R squared? We recall our formula for the slope and intercept coefficient. We've done that when we derived the OLS estimator. So to calculate R squared, we look at the total variation in the actual Y values we are looking at and see how much of that variation is explained by the regression. So the R squared sort of in a way gives you the proportion of variation in the actual Y values about its mean that is explained by the regression. And so we could write the R squared formula as ESS over TSS. So ESS is the explained sum of squares, and TSS is the total sum of squares. So assuming this is the mean by y and this is the actual y we are looking at, this distance here represents the deviation from the mean, of the actual y value from the mean. But you know, if we are working with still on this point, this is the corresponding income, right? What the income predicts using our regression function is actually that y will be at this point. So this is the sort of estimated y. And what is being explained, we're looking at this difference, the difference between y and the mean. But what is explained by the regression is actually this distance, y at minus the mean. And the difference that is not explained is what is captured by our residual. So if we take this and square it and sum it over the different observations, we have the total sum of squares. If we take this, square it and sum it over the different observations of y, of the estimated y we are looking at, we have the explained sum of squares, because this is what the regression is actually explaining. And if we do the same thing for this, we have the residual sum of squares. So we see that TSS, I'll prove that shortly, TSS is equal to the ESS, the explained sum of squares, plus residual sum of squares. So we recall that the actual y value is the estimated y value plus the residual, right? So if we're going to express in deviation from, recall we are trying to show that the total sum of squares is equal to ESS plus RSS. If we take deviation and we just subtract the mean from both sides, let's just do that. So minus y bar, we also subtract y bar from the right hand side so as not to change the equation. So I've taken y bar out of this, so it still leaves this equation balanced. Now remember we represented in deviation from, we use the small letter, right? So if we do this, small y now will be small y at plus this. And if we square both sides and take sums, okay, we square this and take summation, and also do the same thing here. Square and take summation, and this will be summation, this squared plus summation, this squared plus 2 summation, and this will give us 0. So eventually we'll be left with this. The total sum of squares will be equal to the explained sum of squares plus the residual sum of squares. TSS is equal to ESS plus RSS. Okay, so then with this we can calculate our regression coefficient of determination. ESS is what? This summation y at squared, the small y, over TSS summation y squared. So where this is our y, we call consumption is the dependent variable, and this is our x. To get our small y, we just find the mean. We find the mean, and we subtract for each value. So 7.0. Let's assume the mean was 10. I've yet to calculate. We're yet to calculate that. Let's assume the mean is 10. So we'll say 7 minus 10 minus 3. That will be your small y for this. We'll do the same thing here. 6.5 minus 10. You get your small y. 9.0 minus 10. And then you square it, because you're going summation small y squared. You square the value, and so we'll be doing that shortly. And same thing too for the ESS. You get the fitted values first, then square it. And these are the fitted value works. Let's say we estimate our regression function and we arrive at something like y is equal to say 3.0 plus 0.4x. Let's assume this way it works, right? For this observation, for the first observation now, we just put in our income. Income is 8 million naira. So that our consumption where income is 8 now, 3.0 3.2 and this is 6.2. So for this observation, our fitted y will be 6.2 if this was the regression function we got, and we'll do this for each of them. After getting the fitted y, we then get the deviation of the fitted y from the mean, right? Get those values, square it, then sum. So that, but you see, this is kind of strenuous. There's another way we can go about simplifying this so that we don't have to get fitted values first and then work through it, and we'll be showing that briefly. So want to simplify this, getting this. You recall that small y, right, is this big y at minus this, and remember this is sample regression function, beta 1 plus beta 2 x, right? So if we plug this in, our small y will be beta 1 plus beta 2 xi minus this, and this will be our beta 1 from OLS estimation. We know that beta 1 is y bar minus beta 2 x bar, right? So this is beta 1 plus beta 2 xi minus y bar, okay? And this will be y bar, we take out y bar, right? And then we bring out beta 2, we'll be left with minus x bar plus x. So this is x minus x bar, which is the small x. Now if we square this, it will be having beta 2 squared x squared, and when we take summation of both sides, what we'll be having now is this beta 2 squared summation x and I. So this simplifies our formula to get the coefficient of determination, to get our r squared. Our r squared is simply beta 2 squared summation xi squared over summation yi squared, right? So with this, we don't need to be calculating the fitted values, and we'll just make use of summation xi squared and summation yi squared, which we already make use of when calculating our beta 2. We call beta 2 is summation xi yi over summation x squared. So with this value we made use of when getting this, we can easily compute the r squared, and we'll be doing that shortly. So with that, we can begin estimating our regression function for this example. We have the formula for r squared, slope coefficient, and our intercept coefficient. So with that, we just plug the table and plug it in and get our estimates. So here we need summation xi yi, this deviation. So the first thing is to derive our means. We get the mean for y, that is summation y over n, and we also get the mean for x. Then we compute the deviation from the mean. That is x minus x bar. So when we compute our mean, we say 8 minus the mean and do it for the rest. So same thing to getting our deviation from the mean for y minus y bar. So with that, we can then face this, the multiple of the deviations, then the summation will give us what we need together. Then we also need summation xi, so we square this, okay, and when we sum we get that. And then to get beta 1 we need y bar, which we will have calculated. We need beta 2, which we will have calculated using this, and x bar. Then how about this? We need beta 2 squared, which we will have calculated summation xi squared, which will get summing this, and summation yi squared. So we don't have that here, so we'll put that in y squared. So we square what we have here for each of the observations, then take the sum. And so completing this table, we'll be able to get all the figures we need. Okay, so I've completed the table. Let me talk a little bit about how I went about it. So the first thing to do is calculate your mean for y and for x, and for y the mean is simply summation y over n. The sum of y observations is 111, and we have 10 observations, 1 2 3 4 5 6 7 8 9 10. So 111 over 10 will be 11.1. That's our mean. And to calculate the deviation of y, the y values from its mean, we take 7.0 minus 11.1, we get minus 4.1, 6.5 minus 11.1, we get minus 4.6, and that on and on and on. Same thing for x. The mean of x will be summation x over n. That is 170 divided by 10, which is 17. Okay, so we then start with 8 minus 17 minus 9, 10 minus 17 minus 7, 12 minus 17 minus 5, and on it on and on and on. Then we take the multiplication, that's to get our beta 2, estimated beta 2. We take the multiplication between this and this. So minus 9 times minus 4.1, 36.9, and also to get the squares of this, and to get the squares for the deviation from the y values, we also do that too. And so with this, we have everything we need to calculate our coefficients, to calculate the estimated parameters and our r squared. Summation xy, let me just extract that. Summation xi yi is 168. Summation xi squared is 330. Summation yi squared is 88.9. Okay, so with those three values, we are good to go. Okay, so we begin with the slope coefficient, beta 2, and this is summation xi yi over summation xi squared. And we already said that summation xi yi is 168 divided by our summation xi squared 330. Okay, so our beta 2, taking this over this, will have 0.509. These to 3 decimal places, right? So these are beta 2. Next are intercept coefficients, beta 1, y bar minus beta 2, right? Y bar minus beta 2 x bar, right? And our y bar is 11.1 minus beta 2, calculated it here, 0.509 x bar is 17. Okay, so our beta 1 will be 11.1 minus this times this, and that gives 8.653. Beta 1 will be 2.447. Okay, so this also rounded up to, because we've approximated our beta 2, and that's part of what is influencing this. If we made use of the actual value of beta 2, about 0.509010, something like that. It's kind of long. So if we make use of the actual value, we'll be getting something roughly different, but we still expect to get about the same answer. So this is okay. Okay, then finally, with this we can estimate our regression function. Regression function is this, and this will be 2.447 plus 0.509 x, and So with this regression function, we know that y is the consumption and x is the income. So this shows us that if income say increases by 1 naira, then consumption will be increasing by 0.509 naira. That's roughly 51 kobo. And this is a measure of what economists call the MPC, the marginal price to consume. So change in consumption over change in income. So by what magnitude does consumption increase when income increase? So we see that if income is increased by 1 naira, it also be increased by 0.509 naira. If income increased by say 1 million, so this will be increasing by what? 0.509 million naira. So that's about 509,000 naira. And here we also see under economics term the autonomous consumption. So it's what is consumed when income is 0. These are y-intercept, and if x is 0, you see that y will just be this term completely fades away. So this is your autonomous consumption, and this falls within economic theory too, because economics predicts some sort of positive autonomous consumption, and the MPC too should range, usually assumed and expected to range between 0 and 1, not 0, not 1, and this satisfies that. So we've estimated our regression function. So let's also take note that we are looking at it on average. So it's not always the case, but on average, we expect that as income rises by units, say in naira, we expect consumption on average to increase by 0.509. Some will overshoot, some will be below, but roughly when you take their means, you expect it to be about this. So with that, we've estimated the regression function. Next is to see how well this line fits the data. Does it explain it well? Do we need to add more variables and the likes? And our R squared will give us that measure. So let's quickly calculate our R squared. Okay, so calculating our R squared, beta 2 squared, beta 2, we calculate our beta 2 as 0.509. So this will be 0.509 squared times summation xi squared, which is 330, divided by summation y squared is 8.9. Okay, so our R squared will be 0.509 squared, approximately this is about 0.259 times 330 divided by 8.9. Our R squared will be 85.457 divided by 8.9, and our R squared is finally 0.96, approximating to 2 decimal places. So we see this quite strong. Recall we said R squared usually lies between 0 and 1, and 1 being that the regression perfectly fits the data. So 0.96 is quite high, very high, and that shows us that this regression line fits it quite well. If we are to explain this, we'll say that the independent variable, that's income, because that's what makes up this regression line. That's the only variable we are capturing. The independent variable income explains 96%. Writing this in percentage is about 96%. It explains about 96% of the variation in consumption. So income explains about 96% of the variation in consumption, and this shows that our regression line well fits the data. So with that, we've looked at working through an example using the OLS method, and we also learned about the R squared, and that brings us to the end of this video. If you enjoyed it, please hit the like button, and if you've not subscribed, do subscribe too. Turn on the notifications too by hitting the notification bell, and if you have any comments you'd like to see them, do leave them there. Thank you very much for staying.
Hope you enjoyed the video you just saw. If you want more of our videos, please make sure you subscribe to the channel and click on the notification bell. Now, there is a way to enjoy, to make the best of our YouTube channel, which is to go to the playlist section of every video or of every topic. So what you have to do is just type Economics on YouTube. When the page displays, make sure you subscribe. A bell button appears immediately, so you click on that bell button. Then go to the playlist section. So you are going to see videos, playlist, description, and all of that. So just go to the playlist section, and whatever topic you are looking for, look for the playlist and click on the video. Now, our playlists have the classes arranged in a very chronological manner. So if you want to see a class on ISLM, so it starts from the beginning, the simple ones to the difficult to the complex ones. So if you want to see a video on, let's say, elasticity of demand, so you start from what is price elasticity, so from there then to the basic ones, and on and on. So I'm just telling you that in case you really want to make the best of this YouTube channel. And there's also one thing that I want to add, which is that our YouTube classes may not be enough for you. You may want a regular interaction with the tutors and all of that. So what you just have to do is to check the description of the video. You are going to find a WhatsApp link. So but before you do that, I really have to tell you that clicking that link is going to lead you to one of our schools. It's going to lead to some of our schools. So we have MOG School of Economics on WhatsApp, and we make use of our YouTube channel to run the groups. So the classes are paid for, so you're meant to pay for them. So to join our Econometrics school, so that is 2,500 naira per month, and to join our Microeconomics or Macroeconomics schools, so that is 2,000 naira per month. We also have we don't have schools of mathematical economics because microeconomics has its mathematical aspects as well as macroeconomics. So the mathematical aspect of macroeconomics is treated in the macroeconomics school, and the mathematical aspect of microeconomics is treated with the microeconomics school as well. So I'll see you next time. Thank you very much for watching.